Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 11th century in al-Andalus, the vibrant heartland of Islamic Iberia, marked a peak of Andalusian civilization, a crucible where diverse intellectual traditions converged and flourished. Within this flourishing intellectual landscape, the pursuit of celestial knowledge held profound importance, both for its practical applications in timekeeping, navigation, and agriculture, and for its intrinsic philosophical allure. It was an era when the sky served as an intricate, divinely ordered mechanism whose workings invited meticulous study and sophisticated analysis. The challenges facing astronomers of this epoch were considerable. Lacking the benefit of telescopic observation, their understanding of the cosmos relied entirely on the acuity of the human eye, the precision of their instruments, and the power of their mathematical models. The prevailing Ptolemaic system, while remarkably predictive for its time, contained inherent complexities and approximations that astronomers continually sought to refine. Understanding the precise movements of the planets, the intricate cycles of the moon, and the predictable march of the stars demanded an unwavering commitment to observation and constant drive for greater accuracy in calculation. It was within this dynamic and demanding intellectual environment that Abu Ishak Ibrahim al-Zarkali, known in the Latin West as Azarquiel, emerged as a towering figure. His name resonates through the annals of astronomical history, synonymous with groundbreaking advancements in observational techniques, instrument design, and the very understanding of celestial mechanics. Al-Zarkali was a cataloger of stars and a recorder of observations. He was a transformative force, a scholar whose insights and innovations would shape astronomical practice for centuries, bridging the gap between the inherited knowledge of antiquity and the burgeoning scientific inquiries of the medieval period. His work was deeply rooted in the rich scientific heritage of the Islamic world, drawing upon the accumulated wisdom of Greek, Persian, and Indian astronomers, yet he infused this tradition with a distinctly Andalusian spirit of empirical investigation and mechanical ingenuity. The intellectual milieu of al-Andalus provided fertile ground for such a mind. Cities like Cordoba and Toledo were centers of political power and vibrant hubs of learning, attracting scholars from across the vast Islamic empire and beyond. Libraries were repositories of immense knowledge, and observatories, though rudimentary by modern standards, served as crucial sites for systematic celestial observation. The patronage of rulers and the intellectual curiosity of a sophisticated populace fostered an environment where scientific inquiry was actively encouraged. Al-Zarkali's career unfolded against this backdrop, allowing him to engage with the leading scientific minds of his day and to contribute to a collective enterprise of understanding the universe. He operated within a tradition that valued both theoretical frameworks and practical application, a synthesis that characterized much of the scientific achievement of the Islamic Golden Age. The problems al-Zarkali confronted were fundamental to the practice of astronomy: the accurate determination of celestial positions, the prediction of eclipses, the calculation of sunrise and sunset times, and the creation of reliable calendars all depended on a deep understanding of the complex, often irregular, apparent motions of celestial bodies. The Ptolemaic model, with its epicycles and difference, provided a geometrical framework, but the precise parameters and the integration of observational data remained a significant challenge. Furthermore, the need for instruments that could facilitate these complex calculations and observations with greater ease and accuracy was keenly felt. Astronomers required tools that could translate abstract mathematical relationships into tangible, observable phenomena, and that could aid in the arduous process of data collection and analysis. Al-Zarkali's genius lay in his ability to address these multifaceted challenges through a combination of rigorous observation, sophisticated mathematical reasoning, remarkable mechanical inventiveness. He was deeply committed to the empirical grounding of astronomical knowledge, believing that theoretical models must be constantly tested against the reality of the heavens. This commitment to observation, coupled with his profound understanding of mathematics, allowed him to identify subtle discrepancies in existing models and to propose compelling new solutions. His work was characterized by meticulous attention to detail, a quality essential for anyone seeking to unravel the intricate dance of the cosmos. He sought to verify, refine, and, where necessary, to revise established theories based on his own diligent observations and calculations. His contributions would extend to the very tools astronomers used. The development and perfection of astronomical instruments were crucial for advancing the field, and al-Zarkali's innovations in this area would prove particularly influential. These instruments were the extensions of the astronomer's eye and mind, enabling them to measure angles, track celestial movements, and perform complex calculations with improved precision. The creation of instruments that were accurate and accessible presented considerable challenges, demanding a deep understanding of geometry, mechanics, and the specific astronomical problems they were intended to solve. Al-Zarkali's efforts in this domain directly addressed these needs, providing astronomers with more powerful and versatile tools for their celestial investigations. His legacy is thus intertwined with the practical advancement of astronomical observation and calculation, laying essential groundwork for future generations of scholars who would continue the quest to comprehend the universe. The pursuit of celestial knowledge in al-Andalus, as in the wider Islamic world, was fundamentally tethered to the quality of the tools available to the observer. The astronomer's gaze, however, keen required instruments that could extend its reach, quantify its observations, and translate the ephemeral dance of the heavens into comprehensible data. It was within this vital context of practical instrumentation that Abu Ishak Ibrahim al-Zarkali, a towering figure of the 11th century, made contributions that resonated for centuries, refining and inventing devices that significantly enhanced the astronomer's capacity for both observation and calculation. Al-Zarkali's engagement with astronomical instruments was an active process of innovation, driven by a desire to overcome the limitations of existing apparatus and to create tools specifically tailored to the astronomical questions of his era. The era predated the telescope, meaning that all astronomical data was gathered through direct visual observation, aided by instruments that allowed for precise angular measurements and facilitated complex positional astronomy. The challenge lay in crafting instruments that were accurate, reliable, and adaptable to a range of calculations, from determining the time of day and night to predicting the positions of the sun, moon, and planets. Among al-Zarkali's most significant contributions in this sphere was his work on the saphea. While the astrolabe was a well-established instrument across the Islamic world, al-Zarkali's saphea represented a thoughtful evolution designed for a more streamlined and perhaps intuitive application. The saphea, derived from the Greek word for tablet or leaf, served as a portable astronomical computer. It typically consisted of a flat plate, often engraved with celestial coordinates, upon which a retet, or star map, could be placed. Al-Zarkali's particular genius lay in adapting this design to serve specific computational needs, making it more accessible for a broader range of astronomical tasks. His saphea was crafted to facilitate the calculation of various astronomical parameters, including the rising and setting times of celestial bodies, the azimuth and altitude of stars, and the determination of the Qibla, the direction of Mecca. The elegance of its design allowed for these calculations with a degree of precision that was remarkable for its time, offering a more direct pathway to answers that previously required more elaborate procedures or larger, less portable instruments. The problem addressed was the need for a versatile yet easily manipulated instrument that could perform a multitude of astronomical calculations efficiently. Al-Zarkali's saphea provided a sophisticated answer, becoming a favored instrument for many astronomers, complementing his work on the saphea. Al-Zarkali also made profound advancements with the equatorium. This mechanical device was designed to solve a far more complex astronomical problem, the prediction of planetary positions. The intricate, often irregular movements of the planets in the sky, characterized by their retrograde motion and varying speeds, pose a significant challenge for astronomers. While planetary tables, or ZIGES, provided ephemerides, or calculated positions for specific dates, the equatorium offered a means to mechanically model these movements and determine planetary positions for any given time. Al-Zarkali's equatorium was a sophisticated geared mechanism that, once set with the known parameters of planetary orbits, could be manipulated to show the past, present, or future positions of the planets. This was a considerable leap forward from purely tabular methods, allowing for dynamic visualization and calculation of planetary motion. The equatorium was particularly adept at handling the complexities of planetary epicycles and difference, the geometric models used to describe their orbits. By translating these complex mathematical relationships into a physical, mechanical system, Al-Zarkali provided astronomers with an unparalleled tool for understanding and predicting the intricate ballet of the solar system. The problem it tackled was the laborious and error-prone nature of calculating planetary positions using only tables and manual arithmetic, a process that could be immensely time-consuming and susceptible to cumulative errors. Al-Zarkali's equatorium offered a more direct, visual, and potentially more accurate method, serving as a mechanical atlas of the heavens. The innovation inherent in both the saphea and the equatorium lay in their specific design features and the astronomical problems they were engineered to solve. Al-Zarkali's saphea, for instance, was a refined instrument for practical, everyday astronomical computations, making complex tasks more manageable. The equatorium, on the other hand, represented a significant step towards mechanical computation, bridging the gap between abstract mathematical models and tangible, predictive devices. These instruments were practical tools forged from a deep understanding of observational needs and mathematical principles. Their portability and relative ease of use meant astronomical knowledge and the capacity for precise calculation became more widely accessible to scholars. Al-Zarkali's dedication to refining these instruments underscored a fundamental aspect of his scientific approach, a profound appreciation for the synergy between theoretical understanding and practical application. He recognized that advances in astronomy were inextricably linked to the development of more sophisticated observational and computational tools, and he dedicated his considerable talents to advancing this crucial aspect of the scientific enterprise. These instruments, born from his ingenuity, became vital conduits through which the complex phenomena of the cosmos could be measured, understood, and predicted, solidifying his reputation as a master craftsman of astronomical knowledge. The celestial sphere, a realm of predictable yet awe-inspiring motion, presented astronomers with a persistent challenge of the gradual, seemingly imperceptible shift in the positions of the stars, and the timing of astronomical events. For centuries, scholars relied on established tables, the Zij, to chart the heavens, to predict planetary conjunctions, and to mark the passage of time. Yet, as observation grew more precise, the limitations of these inherited records became increasingly apparent. The Ptolemaic system, a cornerstone of astronomical thought for over a millennium, and the subsequent Persian tables, while monumental achievements in their own right, carried accumulated inaccuracies. These discrepancies impacted the ability to navigate by the stars, to accurately determine the seasons, and to comprehend the fundamental rhythms of the cosmos. At the heart of this challenge lay the phenomenon of the precession of the equinoxes, a slow, cyclical wobble of the Earth's axis that alters the apparent position of the stars over vast stretches of time. The rate of this precession, approximately 1 degree every 72 years, meant that tables calculated centuries earlier could no longer perfectly align with contemporary observations. Imagine a meticulously crafted map of a coastline, perfectly accurate when drawn, but over generations, subtle geological shifts render its details slightly askew. This was a predicament faced by astronomers. Their maps of the sky, while conceptually sound, were beginning to drift from the territory they were meant to represent. The problem was compounded by the sheer difficulty of undertaking the extensive, painstaking observations required to recalibrate these celestial charts. It demanded immense dedication and the availability of instruments capable of capturing minute positional differences with unprecedented accuracy. Abu Ishak Ibrahim al-Zarkali, a figure whose name resonates with the very essence of empirical astronomical inquiry, confronted this issue with characteristic rigor. He embarked on the monumental task of creating a new set of astronomical tables, a work that would come to be known as the Zij al-Jadid, the New Tables. This endeavor represented a fundamental reevaluation of celestial mechanics, grounded in a renewed commitment to direct observation. Al-Zarkali understood that the path to more reliable astronomical predictions lay in the meticulous gathering of new data, collected using the refined instruments he so expertly designed and employed. His approach was a testament to the scientific method in its nascent, yet powerful, form: observe, measure, calculate, and revise. The creation of the Zij al-Jadid was an undertaking of immense scale and intellectual fortitude. Al-Zarkali meticulously observed the positions of the sun, moon, and planets, charting their movements with a precision that surpassed previous efforts. He focused on refining the parameters for the solar and lunar tables, recognizing that accurate predictions of eclipses and the positions of these most visible celestial bodies were paramount for both scientific understanding and practical applications like timekeeping and calendar construction. His work on the solar tables, for instance, provided a more accurate determination of the solar year, accounting for subtle variations in the Earth's orbital speed. Similarly, his lunar tables offered improved calculations for the moon's complex path, a crucial element for understanding tidal patterns and for religious observances that relied on lunar cycles. Al-Zarkali's Zij al-Jadid addressed the issue of precession with a new level of accuracy. He re-evaluated established rates through his own observations. This led to a revised understanding of the rate of the precession of the equinoxes, incorporating the accumulated drift that had rendered older tables less reliable. His calculations for this phenomenon, though not presented in the highly abstract symbolic language of later centuries, were deeply embedded in the numerical data of his tables, representing a significant refinement of the accepted astronomical parameters. The resulting tables were a testament to his empirical prowess, offering a more faithful representation of the celestial clockwork as it appeared in his own time. The impact of the Zij al-Jadid was profound, extending far beyond the academic circles of al-Andalus. These tables were destined for a wider audience, transcending geographical and linguistic barriers. Their superior accuracy and the comprehensive nature of their data made them an indispensable tool for anyone engaged in astronomical pursuits. They represented a tangible leap forward, providing a more dependable framework for understanding and predicting celestial events. The dedication to empirical verification, the painstaking measurement, and the careful calculation that characterized the creation of these tables set a new standard for astronomical work. Al-Zarkali's contribution lay in refining the very process by which astronomical knowledge was acquired and validated. His work provided a more accurate lens through which to view the universe, a lens that would prove invaluable to generations of scholars who followed, shaping the trajectory of astronomical inquiry for centuries to come. His work represented a powerful instrument for celestial navigation and calendrical precision, qualities that ensured its dissemination across diverse scholarly communities. The practical utility of these astronomical findings was amplified through the creation of comprehensive tables, meticulously compiled to offer reliable data for astronomers and mariners alike. These tables were dynamic tools, born from a deep engagement with the cosmos and a commitment to empirical accuracy. The culmination of this effort, often referred to as the Toledan Tables, emerged as a pivotal nexus for scientific exchange. These tables were a synthesis of advanced Islamic astronomical knowledge rendered accessible and applicable. Scholars across different cultural spheres required accurate astronomical data to advance their own understanding of the heavens and to develop more precise navigational tools. Existing tables, often derived from less rigorous methodologies or based on older, less refined observations, presented limitations for those seeking greater precision in their celestial calculations. The demand was for a system that reflected the most current and accurate understanding of planetary motion, solar and lunar cycles, and stellar positions. Al-Zarkali's solution lay in the sheer quality and comprehensiveness of his tables. They provided a sophisticated framework for calculating positions of celestial bodies with an unprecedented degree of accuracy for the time. This was achieved through a combination of refined observational techniques, advanced mathematical models, and a systematic approach to data compilation. The tables offered a standardized and reliable source of information, a significant improvement over the fragmented and often inconsistent data available elsewhere. Their creation addressed a fundamental need within the scientific community, the requirement for dependable astronomical data that could be used for practical applications and further theoretical development. The genius of al-Zarkali's contribution extended to its remarkable portability in its adaptability to different intellectual environments. The Toledo Tables were translated from Arabic into Latin, a monumental undertaking that unlocked their potential for a vast new readership. This translation was a crucial step in bridging the intellectual divide between the Islamic world and Christian Europe. It allowed scholars in the latter to access and build upon the sophisticated scientific heritage developed in the former. The process of translation and adaptation was itself a testament to the table's inherent value and the recognized authority of al-Zarkali's work. The impact of this dissemination was profound. The Toledo Tables became a cornerstone of astronomical study in medieval Europe. They were utilized by astronomers, astrologers, and navigators, influencing the development of European astronomy for centuries. The availability of such accurate and comprehensive data facilitated advancements in celestial mechanics, improved timekeeping, and enhanced the accuracy of maritime navigation, which was crucial for exploration and trade. This cross-cultural transfer of knowledge exemplifies the power of scientific endeavor to transcend political and religious boundaries, fostering a shared intellectual heritage. The enduring legacy of the Toledo Tables lies in their role as a conduit for scientific progress. They familiarized European scholars with advanced mathematical and observational techniques from the Islamic scientific tradition. This exposure stimulated further research and innovation, contributing to the intellectual ferment of the later medieval period and paving the way for the scientific revolution. The tables served as a tangible demonstration of the power of empirical observation and rigorous mathematical analysis, principles al-Zarkali championed throughout his career. Their adoption and adaptation by European scholars underscore the universal language of science and the interconnectedness of human intellectual pursuit. The meticulous nature of their creation and the subsequent broad adoption of the Toledo Tables highlight a pivotal moment in the history of science, where sophisticated astronomical knowledge from one civilization directly informed and accelerated the scientific development of another, demonstrating a powerful continuity in the human quest to understand the cosmos. The celestial sphere, a realm of predictable cycles and profound mysteries, presented a persistent challenge to ancient and medieval observers. Understanding the intricate dance of the sun and moon, particularly the phenomena of eclipses and the subtle variations in their perceived movements, was paramount. These events held deep societal significance, dictating calendars, influencing religious practices, and fueling a desire to decipher the cosmos's underlying order. The problem al-Zarkali confronted was a need for a more accurate and predictive model of lunar and solar behavior, moving beyond the approximations that had long prevailed. Al-Zarkali's approach to these celestial phenomena was rooted in a profound commitment to empirical observation, a hallmark of the scientific tradition he inherited and advanced. He dedicated himself to meticulously recording the positions and movements of the sun and moon over extended periods. This painstaking process allowed him to identify subtle deviations from uniform motion that earlier models had often overlooked or smoothed over. His observations were an active interrogation of the heavens, seeking to uncover the precise mathematical relationships governing celestial bodies. A significant aspect of al-Zarkali's work focused on the prediction of eclipses. The ability to foresee these dramatic celestial events was a testament to the growing sophistication of astronomical calculation. Al-Zarkali's tables, particularly those compiled for the Toledo Tables, offered improved methods for calculating the timing and duration of solar and lunar eclipses. This precision stemmed from his refined understanding of the moon's orbital path, including its varying speed and its elliptical nature. He recognized that the moon's apparent velocity across the sky was variable, a crucial insight for accurate eclipse prediction. His investigations into the moon's orbit led him to a deeper appreciation of its irregularities, while the prevailing Ptolemaic model, with its epicycles and difference, offered a framework. Al-Zarkali's detailed observations suggested a need for refinement. He contributed to a more nuanced understanding of the lunar anomaly, the variation in the moon's apparent speed caused by its eccentric orbit. His work provided observational data that supported the idea of a non-uniform circular motion, a step towards a more accurate representation of the moon's path. This focus on the moon's apogee, the point in its orbit farthest from the Earth, and its period of revolution, allowed for more precise calculations of its position at any given time. Al-Zarkali's contributions extended to the solar phenomena as well. He meticulously tracked the sun's apparent path through the ecliptic, refining measurements related to the solar year and the obliquity of the ecliptic. The accuracy of his solar tables was essential for establishing precise calendar dates and for understanding seasonal variations. His work provided a more accurate determination of the tropical year, the time it takes for the sun to return to the same position in the cycle of seasons, a measurement fundamental to agriculture and timekeeping. The significance of al-Zarkali's work on lunar and understand solar phenomena lies in its empirical foundation and its contribution to the development of orbital mechanics. He presented theoretical constructs grounded in a vast corpus of observational data. This emphasis on empirical evidence was critical in advancing astronomical understanding. His refined calculations for eclipses, for instance, were practical tools that demonstrated the power of precise observation and calculation. The meticulous nature of his observations and the resulting improvements in predictive accuracy represented a considerable leap forward. By identifying and quantifying the subtle variations in celestial motions, al-Zarkali provided astronomers with more reliable data and more sophisticated methods. This empirical rigor laid essential groundwork for future investigations into the complex dynamics of the solar system. His work offered a more faithful representation of celestial reality, embracing the observed complexities of planetary motion. His detailed observations of lunar inequalities, for example, provided crucial evidence for the non-uniformity of celestial movements. This empirical evidence was vital for astronomers who sought to develop more accurate models of the solar system. The ability to predict eclipses with greater certainty, a direct outcome of his refined calculations, showcased the practical utility of advanced astronomical knowledge and the power of a scientifically grounded approach to understanding the cosmos. These achievements cemented his reputation as one of the preeminent astronomers of his era, a master of both observation and calculation. His legacy in this domain is one of enhanced precision, a more profound understanding of celestial mechanics, and a testament to the enduring power of empirical inquiry in unraveling the universe's intricate workings. The precise, measured observations and meticulously crafted tables emanating from al-Zarkali's observatory documented the heavens and provided a robust scaffolding upon which future astronomical understanding would be built. His work served as a vital conduit for the transmission of sophisticated astronomical knowledge, fostering a lineage of inquiry that would span centuries and continents. The challenge for subsequent generations of astronomers was to refine the understanding of celestial mechanics, to push the boundaries of predictive accuracy, and to integrate the growing body of empirical data into coherent theoretical frameworks. Al-Zarkali's unique contribution lay in furnishing that essential empirical foundation, a collection of data and computational tools of unparalleled quality for his epoch. The instruments he developed or refined, such as the improved astrolabe, enabled astronomers to gather observations with a degree of precision that had previously been elusive. This enhanced observational capability was paramount. It allowed for the direct measurement of celestial positions and movements with greater fidelity, offering a more faithful representation of reality than abstract geometrical models alone could provide. His tables, the fruits of these rigorous observations and calculations, became indispensable resources. They offered astronomers a ready means to predict planetary positions, eclipses, and other celestial phenomena, thereby facilitating further study and testing of existing theories. This meticulous documentation of the cosmos, characterized by its empirical grounding and computational sophistication, directly addressed the era's pressing need for reliable astronomical data. The influence of al-Zarkali's work extended outward from al-Andalus, permeating the intellectual currents of both the Islamic world and, subsequently, Europe. Within the broader Islamic scientific tradition, astronomers like Ibn al-Shadia in Damascus, working centuries later, benefited from the legacy of precision that al-Zarkali helped establish. While Ibn al-Shadia developed his own innovative models for planetary motion, particularly the lunar theory, his work implicitly built upon the tradition of empirical observation and detailed calculation that al-Zarkali exemplified. The very expectation of accuracy and the availability of sophisticated observational techniques were part of the intellectual inheritance passed down through scholarly networks. The transmission of al-Zarkali's knowledge to Europe was a more complex, yet profoundly impactful process, often occurring through translations and adaptations of his works. His astronomical tables, known in Latin as the Toledan Tables, became widely disseminated throughout medieval Europe. These tables, compiled and revised by scholars in Toledo after the city's reconquest, drew heavily on the astronomical data and methods pioneered by al-Zarkali. European astronomers, from the 13th century onwards, relied on these tables for their calculations and for understanding planetary movements. This access to high-quality astronomical data was transformative, providing a crucial resource for those seeking to understand and advance celestial science in a European context. Figures such as Regiomontanus, a pivotal astronomer and mathematician of the 15th century, directly engaged with the tradition of al-Zarkali's work. Regiomontanus, in his own astronomical tables and writings, acknowledged the importance of accurate observation and calculation, a principle deeply embedded in al-Zarkali's legacy. The European Renaissance witnessed a renewed emphasis on empirical observation and mathematical rigor, and the Toledan Tables, with their al-Zarkali-derived precision, served as a benchmark and a source of inspiration. They provided a foundation for astronomical practice grounded in observable reality, surpassing many earlier, more philosophically driven approaches. A significant testament to al-Zarkali's enduring influence appears in its connection to Nicolaus Copernicus. While Copernicus developed his heliocentric model independently, his work was shaped by the cumulative astronomical knowledge and the high standards of observational accuracy cultivated over centuries. The data and methods available to Copernicus, including those derived from the Toledan Tables and the broader tradition of Islamic astronomy they represented, provided the empirical context for his revolutionary ideas. The need for new model arose, in part from persistent discrepancies in planetary predictions generated by Ptolemaic models, discrepancies that al-Zarkali's work had sought to mitigate through enhanced precision. Copernicus's ability to refine his heliocentric system relied on the availability of accurate observational data to test and validate his theories. The legacy of meticulous observation and calculation, championed by al-Zarkali and passed down through generations, contributed to the pool of knowledge that informed Copernicus's epochal shift in astronomical thought. The pursuit of accuracy, a hallmark of al-Zarkali's scientific endeavors, represented a fundamental commitment to understanding the cosmos as it truly presented itself, a commitment that paved the way for paradigm shifts in scientific understanding. His efforts established a precedent for the kind of detailed, empirical work that would characterize the scientific revolution, demonstrating how precise measurement and calculation could lead to profound insights into the structure of the universe. His tables and instrumental innovations provided the tangible tools and the intellectual framework necessary for astronomers to question existing models and to formulate new ones, grounded in a deeper appreciation for observable celestial phenomena. This cross-cultural transmission of scientific rigor underscores the interconnectedness of intellectual progress and the profound impact of a single scholar's dedication to precision. The impact of al-Zarkali's work on later astronomy illustrates how scientific progress is a cumulative endeavor. His dedication to observational accuracy and the development of reliable astronomical tools provided a critical stepping stone for subsequent generations. The challenge of accurately predicting celestial movements, a persistent problem throughout history, found a more robust solution through his meticulous efforts. His tables, representing a significant advancement in predictive power, became indispensable resources for astronomers across different cultures and eras. Abu Ishak Ibrahim al-Zarkali's enduring scientific significance lies in his profound impact on the trajectory of astronomical observation and calculation, a testament to a mind deeply engaged with the mechanics of the cosmos. His pursuit of accuracy, a guiding principle throughout his career, established a new paradigm for astronomical practice, influencing scholars for centuries to come. The persistent challenge of precisely predicting celestial phenomena, a central concern for astronomers across civilizations, found a more refined answer through his dedicated efforts. Al-Zarkali's meticulously constructed astronomical tables represented a substantial leap in predictive capability, becoming invaluable resources for scholars working in diverse cultural and temporal contexts. The lineage of scientific inquiry, tracing a path from the intellectual flourishing of the Islamic Golden Age to the transformative era of the European Renaissance, unequivocally demonstrates how the precision al-Zarkali champion became a fundamental building block for subsequent advancements. His contributions expanded the existing body of astronomical knowledge and cultivated an ethos of empirical investigation, an approach proving indispensable for the paradigm-shifting scientific discoveries that would follow. The instruments he refined and the tables he compiled offered a more reliable framework for understanding celestial mechanics, serving as a critical foundation upon which later astronomers could construct their own theories and observations. Consider the problem of planetary motion. For centuries, scholars grappled with the complexities of epicycles and difference, seeking to reconcile observational data with theoretical models. Al-Zarkali, through his rigorous observational campaigns and the subsequent construction of his celebrated Toledan Tables, provided a significantly improved set of parameters and predictions. These tables, however exceeding the accuracy of their predecessors, offered a more faithful representation of planetary positions and movements. The very act of compiling such comprehensive data, cross-referenced and refined through repeated observation, embodies a commitment to empirical validation that sets his work apart. This dedication to verifiable data, rather than purely theoretical speculation, was a hallmark of his scientific methodology. The dissemination of al-Zarkali's work played a crucial role in bridging intellectual traditions. Translated into Latin and widely adopted throughout Europe, his tables and astronomical insights became foundational texts for generations of European astronomers. Scholars like Johannes de Sacrobosco and later figures who contributed to the Copernican revolution, implicitly or explicitly, built upon the groundwork laid by al-Zarkali. His sophisticated understanding of mathematical astronomy and his practical advancements in instrument design empowered these later thinkers, providing them with the tools and the observational data necessary to challenge existing cosmological models. The accuracy embedded within his tables allowed for more precise testing of astronomical hypotheses, a vital step in the evolution of scientific thought. Al-Zarkali's influence extended to the very instruments used for observation. His improvements to the astrolabe, a sophisticated astronomical instrument of the time, enhanced its precision and usability. The astrolabe, capable of determining latitude, time, and the positions of celestial bodies, was a vital tool for navigation and astronomical study. Al-Zarkali's modifications, and perhaps the development of new types of astrolabes, reflect a deep understanding of both its theoretical underpinnings and its practical application. These refinements made celestial measurements more reliable, contributing directly to the improved accuracy of astronomical tables and the broader understanding of celestial mechanics. This iterative process of observation, calculation, and instrument refinement is central to the story of scientific progress. The intellectual environment of al-Andalus, where al-Zarkali lived and worked, was a fertile ground for scientific innovation. This period saw a remarkable synthesis of Greek, Roman, Persian, and Indian scientific traditions, interwoven with original Arabic scholarship. Al-Zarkali stood at the apex of this intellectual synthesis, drawing upon the accumulated knowledge of past civilizations, while forging new paths through his own empirical investigations. His work exemplifies the vibrant cross-cultural exchange that characterized this era, demonstrating how diverse intellectual currents could converge to produce groundbreaking scientific achievements. The transmission of his knowledge westward facilitated a critical continuation of this scholarly tradition. The enduring value of al-Zarkali's contributions can be appreciated by considering the shift in emphasis he helped to foster. Earlier astronomical traditions often relied on established theoretical frameworks, while al-Zarkali's approach prioritized meticulous observation and data-driven refinement. This focus on empirical evidence, on what could be directly measured and verified, was a crucial development in the history of science. It laid the groundwork for the scientific method as we understand it today, emphasizing the importance of testing hypotheses against observable reality. His tables were products of a rigorous, evidence-based methodology. The legacy of al-Zarkali is also one of intellectual perseverance. The sheer scale of his astronomical tables, the meticulousness of his observations, and his continuous efforts to refine astronomical models speak to a profound dedication to his craft. He confronted the inherent complexities of celestial mechanics with a spirit of inquiry and a commitment to precision that transcended the limitations of his time. His work served as a beacon, illuminating the path for future astronomers and mathematicians, demonstrating the power of sustained, rigorous investigation. In essence, Abu Ishak Ibrahim al-Zarkali was a pivotal figure in the history of astronomy. His innovations in astronomical instruments, his creation of highly accurate celestial tables, and his unwavering commitment to empirical observation fundamentally advanced the field. He acted as a crucial conduit, transmitting and enhancing the astronomical knowledge of previous eras, while simultaneously laying essential groundwork for the scientific revolution that would transform the world. His legacy is embedded in the very fabric of modern astronomy, a testament to the enduring power of precision, observation, and intellectual curiosity. The standards of accuracy he established continue to resonate, reminding us of the profound impact one individual could have on the collective human understanding of the universe. His life's work represents a pinnacle of scientific achievement, a synthesis of tradition and innovation that propelled celestial science forward with remarkable force and lasting consequence.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.